The broadcast is now starting.
Hello everyone, thank you for joining us today for Permanganate 101 webinar with our speaker John Boll with Carus. I'm Ashley Clark, Marketing Specialist, also with Carus. A few housekeeping items before we get started. All attendees are in listen-only mode to help cut down on any background noise. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through GoToWebinar, we will receive a report with the question and your contact information to follow up directly after the webinar. If you are interested in receiving a PDF or recording of the presentation, please contact us. We encourage you to share the recording within your network. Here are a few ways to find us. We have listed our website and general sales and marketing email address, as well as my email address. Do you receive our email blast for upcoming webinars, presentations, trade shows, and technical information on our various solutions? If not, sign up on our website. You can find the Join Our Email list on any landing page on the right-hand side. Be sure to select the industry when signing up to ensure you receive the most targeted information for your needs. And we can't forget to mention our social media platforms. We encourage you to connect with our Carus Corporation page as well as our team members on LinkedIn, where we are often sharing upcoming events, including webinars, industry articles or news, sharing relevant posts from other industry experts, and more. Listed here are links you can visit for upcoming webinars and also our website. At this time, I would like to take the opportunity to introduce our speaker, Mr. John Boll. John is the Global Technical Program Manager for Carus Corporation. He has been with Carus for over 45 years, serving in a variety of sales and marketing positions. The Technical Service Department provides chemistry and applications customer support, including on-site lab testing and plant-scale startup and troubleshooting services. John earned his bachelor's in engineering from Purdue University. He is also a member of the Water Environment Federation and the American Water Works Association, where he served as the AWWA Illinois Section Chair from 1992 to 1993.
All right, thanks Ashley for getting us started, appreciate it. This is actually the first webinar that we've done where you're driving and I'm speaking, right? So we'll have some fun, right?
Yeah.
Okay. Welcome to everybody. I'm John Boll, and over the next 45 minutes or so, we're going to cover some very basic background information on our permanganate products. And I actually have a pathway that I'm going to try and follow here. You can see it on your screen. I'm going to do a very quick introduction to our products for those of you who may not already be familiar with them. And then I'm going to talk a little bit of chemistry. Sorry, that comes along as part of the deal. We'll talk about oxidation chemistry in general and then permanganate chemistry specifically. And then I'll start talking about how oxidants are used. I'll introduce the four major categories of end-use applications for oxidizing agents. And then I'll just introduce you to a wide variety of current and historic permanganate uses in both municipal and industrial applications. So let's start with our permanganate products. The historic workhorse of the permanganate world is dry crystalline potassium permanganate. Potassium permanganate is the product that is manufactured at most manufacturing locations because it is relatively easy to drop out of solution at a very, very high purity. So our crystalline dry products are marketed under our brand name Carus, and we can offer a variety of different grades of this product as we manufacture and manipulate it in our plant here in LaSalle, Illinois. So typically the first product that drops out is what we call technical grade material. Technical grade is always at least 98% purity. and it is a great product to use, in particular if you're going to be mixing the permanganate as a water solution and then feeding it as a aqueous solution or an aqueous liquid. The sister product to technical grade is what we call free-flowing grade. So technical grade material is hygroscopic. That means that it likes to pick up moisture from the air. And so when relative humidity is high, such as in water plants or wastewater plants, it will have a tendency to lump or cake together after it's been exposed to the air. So we recognized this very early on, and back in the late 1960s, we developed a product that we call free-flowing grade. It is essentially technical grade material in which we blended about 1% of a desiccant in with it to coat the crystals and discourage them from sticking together in high humid areas. Now, because we're adding that desiccant in there, the purity drops slightly by 1%, so the guaranteed assay on free-flowing material is 97% purity. Now, technical grade and free-flowing grade are by far the largest volume products that we manufacture and sell. But there are some specialty grades as well. So for example, we have pharma grade, which is conforms to the US Pharmacopoeia standard, which is always 99% purity. And then there are some other individual specifications that have to be met under that particular grade as well. Very similar to that is the ACS reagent grade material. It also must be at least 99% pure. And that's the material that is typically packaged in 1 or 5 pound containers and is used in laboratory for different types of analytical procedures. These are all available and packaged in a variety of different types of sealed containers. There are some interesting offshoots of these dry crystalline products that we also offer for specific applications. One of those is the Carus potassium permanganate nuggets. The nuggets are a slightly larger particle size. They're very irregular in size, as you can see from the photo, but they're very nice to use when you need to broadcast them, for instance, to a pond or a lagoon, in particular if that pond or lagoon is outdoors, where it might be just a little bit windy. So this is a less dusty material, and because the nuggets are heavy, when you broadcast them into the lagoon or pond water, they will tend to sink and treat the water all the way through the water column, and depending on the depth, they will often make it all the way down to the bottom of the lagoon. If that's where the problem is occurring, then we can treat down there at the lower depths. Another specialty product is what we call potassium permanganate, or CR tablets. These CR stands for controlled release. They look like the hockey puck that you see there on the right-hand side of the slide. And these are designed to be released when you place them in flowing water. The advantage here is that sometimes you're in an area where water utilities are not available or electric utilities are not available, and therefore you don't have the capability of using some type of chemical feed system to meter out the permanganate. In this case, you put the tablets into some type of perforated container. Could be a solid container, could be like the mesh bag you see on the left-hand side of this screen. And then as the water flows by, it slowly dissolves them and gives you a small amount of permanganate concentration to do very fast oxidation reactions. The amount of permanganate released and the life of a tablet depends on the speed of the water flowing past it. So a higher velocity water dissolves the pellets more quickly. A slower moving water dissolves them slowly. If we move away from the dry crystalline products, then we can talk about pre-mixed concentrated liquid products that are available under our brand name Carus. They are available in 2 different types of concentrations. The first is 80% active ingredient, and the second, Carus C, is available as a 40% active ingredient. In the case of both the dry crystalline material and these concentrated liquids, they're very stable when they're held in or stored in their sealed package containers. The stability really is measured in months and in years, so that they can be used stored and used over a long period of time. I would just point out too, this is a good spot to mention. On the right-hand side, you see a sample of water that's been treated with potassium permanganate or sodium permanganate, and you can see that it has a very distinct purple or pink color. So whenever permanganate's present in water, you know that it's there because of this color that you can visually see. So let's talk a little bit about what permanganate really is. The permanganate ion is MnO4 -1, and it is available when you manufacture it in a variety of different salts. The two most common salts are the potassium permanganate, KMnO4, and the sodium permanganate, NaMnO4. But there are other types of cationic salts that you can make as well. Permanganate is an oxidizing agent, and it's what we consider to be a stable oxidizing agent. That means when we manufacture it, we can put it into a drum, it can be stored, it can be delivered to the customer site and used at some time in the future. It does not have to be generated at the site where it's going to be used. And we make permanganate by starting with manganese dioxide ore. It's a material that is mined out of the ground. Manganese is a common constituent of soils around the globe. And we add energy and oxygen to that manganese dioxide and raise the potential of it up until we get to the permanganate ion, MnO4. Now, when a customer buys permanganate and uses it, they are essentially extracting that energy and that oxygen out of the permanganate, and the permanganate returns to almost its original MnO2 form. From a chemistry standpoint, permanganate can be sort of lumped into one of two buckets. The first is, of course, that permanganate is a manganese compound. I mention that in particular because it can be confusing, because magnesium is also one of the common elements. Calcium and magnesium are the constituents of hardness in water supplies, but that's not what permanganate is. Permanganate is a manganese compound and is often regulated and controlled under that category. Permanganate is also an oxidizing agent. As I mentioned, we manufacture it by adding oxygen and energy to the manganese oxide ore to produce it. So an oxidizing agent, in very, very simple terms, is really nothing more than a form of energized oxygen that's being delivered to the site where it's going to be used. That energy and that oxygen can be extracted by the customer who's going to use the product. Now, oxidation as a term shouldn't really surprise us much. It's derived from the word oxygen. And of course, we should be familiar with oxidation reactions because we live in a world where our atmosphere is highly oxygenated, so we're surrounded by oxygen every day. So some of the more common oxidation reactions you might be familiar with is rusting. So ferrous metals reacting with the oxygen in the air to form iron oxides and giving you that distinct reddish brown rust color. That's a very slow process, can take many, many days, many, many years for that rust to form. Then there's some oxidation reactions that are very, very fast. An example of that might be this burning match, where the reaction is so fast that we're releasing energy in the form of both heat and light. For the most part, oxidation reactions always release some energy, usually in the form of heat, but most of these reactions are in such dilute solutions, in particular water, that you never see any of the temperature change that is released. Now, to the chemist, they're a little bit more exact when they talk about oxidation chemistry. And to them, it really is an issue of transferring electrons from one compound to another. So there's always one compound that's releasing electrons and one compound that's accepting them. So oxidation is always coupled with a process called reduction. And if you read about these sort of reactions, you will see it often referred to as oxidation reduction reactions. Here's a very common, very simple reaction that demonstrates where oxidation and reduction are paired together. So we have the permanganate ion, that's the MnO4-1 in solution that would be pink or purple in color. And that reacts with the manganese to produce manganese dioxide. I see that the arrows have moved and are not really going to the right location. They should be pointing toward the MnO2 on the right-hand side of that reaction. That MnO2 is a solid material. It's usually yellow or gold in color, can be brown in color, and it precipitates out as a flock material with very high surface area and a slight negative charge. That's the reduction part of it. The oxidation part is the manganese +2, which is dissolved in water. You can't see it. You only know it's there if you test for it. And when it reacts with the permanganate, it also will go to MnO2 as the final endpoint. And it is a very special relationship between permanganate and the oxidation of soluble manganese. Now, there are not only oxidation reactions with inorganic materials, there are oxidation reactions with organic materials, which are carbon compounds, usually represented by compounds of the living cells. Here's an example of an oxidation reaction that is not uncommon for permanganate and organic materials. And by that I mean a complete oxidation reaction would really go to carbon dioxide and water. That's sort of what happens when you have a burning match. But in water plants or water systems where we're using permanganate, we generally don't go that far, or that far to completion in any case. What we have is we have partial reactions that take place where we fragment a large molecule and we cut it up into 2 or 3 or more smaller molecules. And the hope there is that whatever we're trying to accomplish, whether it's taste control or odor control or toxicity removal or color removal, all of that is accomplished by doing this fractionation or this partial oxidation reaction. Now, how does permanganate differ from a lot of other oxidizing agents? Well, permanganate likes to react with very specific organic functional groups. And you can see them here both by diagram and by text. So we have alkenes and alkynes, which are double bonded and triple bonded connections between carbons. Permanganate loves to attack at those points. You have a lot of side chains that permanganate will react with, for instance, alcohol groups, or even sulfur groups or nitrogen groups that might be attached to an organic compound. Oxidation reactions are often pH dependent. The pH can, in fact, control whether or not the reaction happens at all, but mostly it affects how rapidly the reaction takes place. Now, pH conditions are not quite that important in permanganate reactions. You can see that in most cases, the reactions that we work with are going to take place in the pH range of 3 to 12. And in that situation, you have the permanganate ion, MnO4-1, exchanging 3 electrons and going to the manganese dioxide solid that we've talked about previously. There are some cases where if you go to extreme pH conditions, you can change that reaction. So under acidic, very acidic conditions at less than pH 3, for example, the permanganate ion MnO4-1, exchanges 5 electrons and goes to soluble manganese 2. And then finally, under very alkaline conditions, greater than pH 12, it is possible to just automatically lose 1 electron just while the product is sitting in solution. And you go from permanganate, MnO4-1, to manganate, MnO4-2. The fun part about that reaction is the permanganate ion, which is purple or pink in color, changes to a very greenish color when you lose that 1 electron. So let's talk a little bit about about oxidation chemistry. It's really quite versatile and it's really a lot of fun. There are really 2 portions to oxidation chemistry. One is where you're taking small products or converting products from one form into another form, where you're building a molecule or converting or synthesizing a molecule of some type. That's the reactions that you typically find when you go to a textbook and look up oxidation chemistry, because most of the research is done on how oxidants can help you to produce or manufacture some type of active ingredient. Now, in the environmental applications that we'll be talking about, which are typically water purification or air purification, we're generally talking about breaking a large molecule down into its smaller components. So when we're trying to destroy something or try to purify something by removing a contaminant, we're talking about the other side of this equation where we're taking big molecules and breaking them down into smaller ones. I like to categorize commercial oxidation into one of 4 major buckets. The first is that synthesis or purification reactions that I mentioned on the one side of the previous slide. I also include in there industrial cleaning applications. Those are very common for a wide variety of oxidizing agents. Then in the upper right, you can see that oxidizing agents are bleaching compounds. They react with and remove color bodies from different types of materials to turn those materials from colored to white. And there are some permanganate applications where this occurs as well. In the lower right-hand corner, you see sort of a catch-all for me. That's really where I put all the environmental applications from cleaning contaminated soil to purifying drinking water, to deodorizing wastewater, to purifying air supplies. And we'll talk a little bit about those coming up. And then finally, oxidizing agents to one degree or another are a good or a slow type of disinfectant, and they have different kinds of therapeutic applications. Now, in that particular area, I have to let everybody know that the Carus products are not currently registered as biocides with the US EPA or with the FDA. So we're not allowed to promote or sell our products for any type of disinfection or biocidal type of application. So let's talk a little bit about the different types of environmental applications. First, let's start off with soil remediation. It's often referred to as in situ chemical oxidation, ISCO. This is particularly popular when the contamination is due to the dry cleaning or degreasing compounds, trichloroethylene or perchloroethylene. Permanganate reacts with these compounds very readily, reduces them down to innocuous, non-hazardous components, and can be injected subsoil where these materials have collected and may be contaminating groundwater supplies. There are also situations where the contamination might be at the surface. So you can see a slide here where soil material has been treated and mixed into soils at the surface. And there are also cases where you can do an excavation and treat and then put the treated soils back in again. So there are a variety of different techniques that are used for injecting or applying permanganate into contaminated soil to remove trichloroethylene or perchloroethylene. Of course, historically, one of the major applications, and also currently for potassium and sodium permanganates, are the oxidation purification of different drinking water supplies. Drinking water applications really date all the way back to the late 1800s and early 1900s, when oxidizing agents in general were first looked at for water treatment. Now, permanganate can be applied to both surface water supplies and to groundwater supplies. And I like to look at the application reactions in terms of the type of compounds that we're oxidizing. So you'll see that I have them divided into the man-made or naturally occurring inorganic types of chemicals that we're reacting with, and or the natural or man-made organic material that we may be reacting with. There is some overlap between surface water and groundwater when we talk about the inorganic materials. Iron and manganese are the most common that we're oxidizing and removing by precipitating them out as solids, and then our clarification or filtration processes can remove them from the water. You can also see sulfide material in either one of those water sources. And in groundwater supplies, there is some arsenic oxidation and removal and some radium removal. And we'll talk specifically about radium removal because it's a little unusual. There is no oxidation reaction that takes place there, but there is an absorption reaction. When we talk about organic matter, typically groundwater supplies don't have a lot of organic material in them, although you can run into some cases where you might see some colored water, especially if it's from a well that's not very deep and may be influenced by surface contamination. But most of the organic material we see is present in surface water supplies, and it presents itself in terms of taste, off tastes, or off odor types of situations. Disinfection byproducts, so that's the reaction of our disinfectant chlorine with organic compounds to produce trihalomethanes or haloacetic acids or other chlorinated compounds. Permanganate can be used to oxidize those organic materials before the chlorination step to lower that formation. One of the newer organic materials that we're looking at and that permanganate is oxidizing is organics that are produced as algal toxins. Of course, color can often be due to some type of organic material, so color removal is an application. And then there is some very small amount of total organic carbon or natural organic material oxidation that can go on with permanganate as well. So let me go back to our slide that points out that permanganate likes to react with very specific functional groups on organic compounds. So why is this important? Well, it's important because a compound has a specific taste or a specific odor, often because of its structure and because of the functional groups that are associated onto that backbone structure. So it turns out that permanganate is quite effective at controlling tastes and odor compounds, whether they're in water or whether they're in air. And you can see that these functional groups on these compounds can be attacked by permanganate because it likes to go after those functional groups immediately. The nice thing about attacking and eliminating the functional group is that the taste or the odor will go away even if we haven't fully degraded the complete molecule down to CO2 and water. The inorganic oxidation reactions are easier to talk about because there aren't very many of them. I've already mentioned that permanganate is used in particular to remove manganese from water supplies, but it also is used to remove iron. It will oxidize arsenic 3 to arsenic 5, and then arsenic 5 can be absorbed onto the manganese dioxide and removed through the filtration process. And permanganate reacts with hydrogen sulfide or other sulfide compounds to deodorize it and form sulfates as the byproduct. Here is the reaction again with permanganate and soluble manganese, and you can see the formation of the manganese dioxide as a byproduct. That's important to know because, let me say again, the manganese oxide has a very high surface area. It's a flock material and it has a slightly negative charge. Because of those characteristics, it likes to absorb, it has a slightly negative charge. Because of that characteristic, it likes to absorb monovalent or divalent positive cations and remove them from the water supply. Now, there's one very practical application of that currently in groundwater drinking water treatment, and that's the removal of radium-226 and 228. It turns out that radium likes to absorb onto manganese dioxide, and it can then be removed from the system on the plant's filter. So in these particular cases, we're not doing any kind of oxidation with permanganate. We're actually preforming what is called hydrous manganese oxide, or HMO, by reacting permanganate with manganese sulfate, producing the HMO, and then injecting the HMO into the water supply to absorb and remove the radium. But keep in mind, anytime we're treating water or wastewater with permanganate, and we're producing freshly precipitated manganese oxide, we have the capability to absorb and remove certain types of positively charged cations. Now, I want to say a little bit about cyanobacteria or blue-green algae. This is a contaminant, if you want to call it that occurs in an awful lot of surface water supplies, and the water industry has known and been familiar with blue-green algae for many, many, many years because of all of the adverse problems that it can cause in a water treatment plant that I've listed here. But I would look particularly at the fact that they produce unpleasant tastes and odors, and now we know that they also produce different kinds of toxic material when they're growing, especially when they're in very, very high concentrations. So we've known for a long time that permanganate is good for odor control and taste control in water treatment, and it turns out that those compounds are as a result of the growth and activity of algae, and in particular blue-green algae. And we know in most cases, we recognize them from their characteristic, which is often referred to by the terminologies that you see here. And also now with our analytical capabilities, we can identify specific compounds that contribute to those characteristics. All of these that I've listed here, we know that permanganate reacts with very, very quickly and can be removed from water supplies by doing permanganate oxidation chemistry. What we now know also is that these different types of algae can also now produce cyanotoxins. And it turns out that permanganate can, in fact, oxidize some of these toxins as well, but not all of them. Here are our friends in the right-hand column, Microcystis, Anabena, Oscillatoria, all of those that produce different types of tastes and odors. And we can now tie them to particular types of algal toxins. Here's a summary chart that shows that if you have microcystin present, and microcystin is often the most common algal toxin that we run into in the United States, and also antitoxin A. Both of those toxins react readily with permanganate and relatively quickly as well. The cylindrospermopsin and the saxitoxin, unfortunately, are not oxidizable by permanganate and would really have to be removed using a different process, such as carbon absorption. Now, let me just say quickly, where is permanganate added when you're talking about a water treatment system? So here's a diagram of a typical surface water treatment plant, and you can see that permanganate is injected very early in the process, usually in the raw water supply. And we do that for really three particular reasons. One is we need some reaction time. Not all of permanganate's reactions are instantaneous. Some of them may take 20 or 30 minutes, maybe some up to an hour. So we need some time at the front end of a plant in order to be as efficient as we possibly can with our reaction times. Secondly, we know that when permanganate reacts, we produce a precipitated flock material, manganese dioxide. So we want to be able to remove that manganese oxide block in the solids removal steps of the water treatment plant. So typically we like to have all that manganese oxide formed when we go into the flocculation zone, and definitely by the time we get into the sedimentation area. And then finally, sometimes there are other compounds that permanganate can react with. Typically, powdered activated carbon reacts with permanganate. So we try to split the permanganate feed away from the carbon, which may be fed, for instance, here at the rapid mix area. So it gives us some time between the two injection points. In a groundwater supply, there's often not a lot of time, but because we're mostly reacting with iron, manganese, and sulfide, all of those reactions go within seconds to minutes. So the time that it takes from permanganate injection to the water entering the top of a pressure filter and the little bit of time it has in the headspace is sufficient to allow permanganate to do that reaction, convert those materials into solid particles so that the filter will remove them. Now let's switch over to wastewater treatment, and in particular, municipal sanitary wastewater treatment. What we see in wastewater treatment is that there are a lot of sulfur compounds that are produced, and all of these sulfur compounds have very distinctive, unpleasant odor characteristics, and you can see them listed here in the center column. But also what's important here is the column on the right shows you that the amount of these materials in the air only has to be very, very small in order for the human nose to recognize that they are there. So that's the threshold odor level. And so they create quite a difficult situation for plant operators because it doesn't take much of these compounds to produce an unpleasant odor complaint situation. You can see that most of the materials listed here are mercaptans. These are organic sulfur compounds, but you also see hydrogen sulfide listed on here, and permanganate reacts with all of these particular compounds. So where are odors most prevalent in water treatment? Well, they're very volatile, so they like to be released whenever you create turbulence in the system. So any of these situations that you see here, where we're spraying the water or it's falling over a weir trough, it's coming out of an open pipe or going through a partial flume, or in the case of even just aeration processes where we're blowing fine bubble air through the wastewater, all of these situations will strip the odors into the surrounding atmosphere. So instead of identifying permanganate uses in terms of what we're reacting with, because the compounds we're reacting with are only few, we generally talk about wastewater treatment in terms of where permanganate is applied. So here you see a situation where permanganate is being used at the treatment plant itself, typically where the collected wastewater enters the headworks of the treatment process, going through the screening areas. It can also be applied between the primary and secondary clarifiers, where there's often odor produced in the primaries. And then in some recycle streams that they're collected in the plant and returned back to the headworks, we can treat those as well in order to deodorize them. One of the big areas in wastewater treatment for permanganate applications is in sludge drying or dewatering areas. When you concentrate the solids by thickening or by storage and then squeeze the water out of them on some type of mechanical device, you release odors into the air. And the nice thing about permanganate is what you're really buying here is speed of reaction. You may not have very much time for the oxidation reaction to be completed before you actually release the odors. So the fact that permanganate can complete that reaction in a matter of seconds to minutes is one of the advantages of using permanganate. We also use permanganate in collection systems. So collection system odors are quite common when there are long distances or storage of collected wastewater that allow it to go anaerobic and create reduced sulfur compounds. The situation is often in areas where you don't have easy access to them. So bringing in water utilities or electrical utilities may not be possible. These are areas where we can use the CR tablets quite effectively as well. If you do have power and you can run a metering pump of some type, then you can feed, for instance, here using a peristaltic metering pump and provide the correct dosage to the wastewater system. Manhole applications, here is one of those cases where the CR tablets are quite popular and very, very effective. You really control the dose in one of two ways. One is by how many pellets are being submerged into the flow, and the second way is how many bags that you're actually hanging into the flow, depending on the size of the pipe or the size of the wet well that you're trying to treat. Don't forget that wastewater odors and wastewater treatment can occur at industrial sites as well. We're not just talking about municipalities here. And often at industrial sites, you'll see situations where you may have aerated lagoons. Remember that aeration is really good at stripping odor compounds out of the water and into the air. So that's a really great place for adding permanganate. Permanganate and oxygen together are a very, very effective way of controlling odor compounds. And you can treat different types of water bodies from the shoreline using metering pumps or gravity feed, or even in the body of water is large enough from a boat to actually distribute the permanganate around the surface of the water supply. One of the most recent industrial applications where we're treating odors is landfill leachate, especially when the landfill accepts construction waste materials, because often that waste material will contain different types of sulfur compounds. And when the rainwater leaches down through the waste, it leaches that sulfur material out, it goes anaerobic, and the bacteria produce high amounts of hydrogen sulfide. Often we are treating at a collection tank that's on the sanitary landfill site and destroying the odors there. But often the odors are not released until the wastewater is actually transferred, typically to a local municipality. And that can be done by direct piping of the material to the collection system of the municipality, or if there's no direct pipe to the municipality, by way of a tanker truck. And when those two disposal methods are used, odors are often released at the municipal site. So pre-treatment with permanganate is a good way to eliminate that situation. Iron and manganese in particular can also be found in mining leachate waters. So permanganate is used to oxidize and precipitate those compounds. The difficulty here is setting up the controlled feed system so that you can get it out into very, very remote areas. Don't forget that not only do humans generate odorous waste, so do animals. If you are operating a confined space, intensive raising operation, such as hog confinement barns or cattle feedlots, permanganate has been used to control odors from those situations as well. And now let me finish the presentation today by going back and talking a little bit about some of the interesting niche applications for permanganate, industrial applications that fall into these two categories of synthesis and purification and or bleaching types of applications. The first in synthesis is that active ingredients of different kinds of compounds are often manufactured using permanganate as an intermediate oxidation step. Historically, one of the large uses of permanganates were in the production of saccharin, which was a artificial sweetener. That application is no longer as big as it was at one time, but there are still a number of pharmaceutical and agrochemical products that are produced using permanganate oxidation chemistry. There are purification types of applications, including zinc purification, where zinc is being produced from zinc ore, and it's necessary to remove iron and manganese from that from that ore supply in order to get a purified zinc. We have situations where permanganate is used to wash and oxidize impurities in food-grade CO2. And permanganate is also used to produce medicinal nitrous oxide by removing different types of impurities in that gas as well. Permanganate is used in a few interesting bleaching applications. Everything from producing very green phosphoric acid, as you see in the upper right-hand corner, to oxidizing and decolorizing kale and clay that is used for making china. Permanganate is used to make white beeswax that is used to produce candles. And one of the fun applications is using permanganate to remove the blue aniline dye from denim so that you can make different types of washed out or distressed looking blue jeans. Permanganate is used by the aquaculture industry, generally in the United States. This is the catfish industry in the South, the trout industry in the Pacific Northwest, and also the shrimp industry in the Southwest. And this is typically water treatment to remove impurities, to remove algal toxins, to remove taste and odor compounds, so that the fish don't exhibit any of these type of unpleasant tastes or odors. There's also an application where permanganate is used to destroy a product that hatcheries and fisheries use, which is called rotenone, and they use it as a fish toxicant or a fish poison when they're trying to prepare a pond or a lagoon for stocking. And at the end of that application, permanganate is used to destroy that fish toxin and remove it from the water supply. Permanganate is used to treat metal surfaces, to remove scale or dirty carbonaceous smut. And this is typically done in an acid cleaning line where a manufacturer is making ferrous rod or ferrous wire. And the reason you clean the surface of these products is because you're usually preparing them for some type of plating operation further on down the line. And you want that plating material to stick nicely, adhere nicely to the metal surface. So it needs to be clean and slightly rough. This chemistry has also morphed over into the plastics industry. And typically permanganate is used to clean and etch the surface of printed circuit boards just before the copper plating is applied to produce the electrical connections between components or between layers of multi-layered circuit boards. The surfaces can often be industrial. So for instance, heat exchangers in areas where there's a lot of organic material, such as a refinery or a food processing plant, can have organic material build up or organic slime build up on the inside of the equipment, and permanganate is used to remove that organic material. In refineries, they produce a different type of scale. They produce a scale that is referred to as pyrophoric iron sulfide. If it is exposed to the air, it gets hot and can burst into flames. So before you can work on a piece of equipment or open up a piece of equipment that has pyrophoric iron sulfide scale, they will wash it with permanganate solution to destroy that sulfide and get rid of it so that they can do the maintenance that they need. In jet engines, there is often heat scale that is formed during the operation, and when the engine is brought in for maintenance, you need to remove that scale so the maintenance operator can inspect the part and make sure that its integrity is still good. We're doing a lot of work in upstream and midstream oil and gas applications. Most of this is water treatment from the produced water that comes out of the oil wells themselves and involves the oxidation of sulfur compounds or the oxidation of iron. I already mentioned the oxidation and removal of pyrophoric iron sulfide in refineries. And here's one of those cases also where the freshly precipitated manganese dioxide can help by absorbing and removing selenium from different types of water or wastewater streams. So just to summarize then, what we covered today was a little bit about the different types of permanganate products that are available, the fact that they come in different grades that you should be aware of, and the fact that they come in a variety of different packages, from small packages to large bulk type deliveries. Permanganate is used on a large industrial scale for chemical synthesis and purification reactions. It is also used in small niche bleaching applications. And then finally, it is used in a variety of different water and wastewater and air and soil treatment environmental applications where it's very, very effective. So that's the end of my presentation. I'm going to turn it over to Ashley again, and we'll close out the webinar.
Thank you, John. At this time, we will go ahead and start taking questions. While we wait for a few to come in, I'll go ahead and go over this current slide. It shows our sales managers' information along with their contact info. Feel free to reach out to yours in your region. Shown here is our presenter, John's contact info, as well as our sales and marketing contact. Now we'll go ahead and go back and go over some of the questions that we received. Okay, the first question, is it possible to test permanganate's effectiveness for contaminant removal in a specific water or wastewater application?
Yeah, so that's a great question. One of the advantages of permanganate and the fact that it's relatively stable is that you can make up a stock solution and use it in the laboratory to test different types of samples that you may want to deodorize or decolorize or whatever the application might be. So we have available literature pieces that would walk you through doing different types of jar tests on how to prepare a stock permanganate solution for the laboratory, and also discuss a little bit about how we can come out and help you and give you a hand at running on-site laboratory jar tests. And those are always good to run first before you go out into the actual plant site or to some type of pilot application, because it will tell you whether or not a reaction is actually occurring, which means are we in fact doing what we want to do. And secondly, it gives us some idea, it sort of estimates for us what the permanganate demand would be. In other words, how much permanganate might be needed in order to complete the oxidation reaction we want to do. And that's all good information to have up front.
Thank you, John. It looks like we do have one more question. Is there a standard recommendation for permanganate feed equipment?
Well, I wouldn't say that there's a standard recommendation. The dry chemical material itself is usually applied through a dry chemical volumetric feeder. Those are typically helix type feeders because we're usually only applying small amounts, small poundage of permanganate on an hourly basis. I would note that a dry chemical feeder usually has some type of extension hopper associated with it, where you can store permanganate that's being fed. And of course, in that situation, you want to be sure that it doesn't get lumpy or cake in any type of way. So dry chemical feed systems always use free-flowing grade permanganate. The other thing I would say about a dry chemical feeder is that you never, almost never, apply permanganate directly as a dry product. It's always mixed first with water and then delivered to the point of injection as a water slurry or as a water solution. So a dry chemical feeder has various parts. In addition to the feeder, you have the hopper, and then you also have the water dissolving system that comes along with it. If you're using the concentrated permanganate liquids, we use a variety of different types of metering pumps. Typically, there's some type of diaphragm metering pump, or they could be a peristaltic metering pump. And the only thing you need to think about when you're designing a permanganate feed system is that not all materials of construction are compatible with permanganate. So check in advance to see that all of the materials in the pump or the feeder that you're going to use are compatible. And we have a handout sheet, a guideline that will at least get you started thinking about what types of materials are compatible with permanganate and which ones are not.
Okay, and we do have one that just came in. Would permanganate greatly break down the TOC in groundwater supply as to not produce THMs when subsequently treated with chlorine?
Yes, there is enough research for us to know that the permanganate effect of THM control due to the oxidation of the organic material falls somewhere between 5% effective, which is not very effective at all, to as much as 40% effective. So there could be a 5% to 40% reduction in THMs depending on what that precursor material is and how readily the permanganate reacts with it. A lot of the situations where we're doing THM control had to do where chlorine was initially being applied early in the process to, say, the initial groundwater or the raw water, and therefore there was a lot of contact time and a high chlorine dosage where the water was the dirtiest in terms of TOC. By delaying that chlorine addition and substituting permanganate at the beginning of the process to do the things that chlorine was originally doing also contributes to lowering the amount of THMs that are formed.
Okay, I think that's it. Thank you again, John, and thank you everyone who tuned in to watch. Have a great day.